So the matrix array currently offered in 64, 128, or 256 channels. It's a complete modular assembly, so you can mix and match short probes, long probes, 2D arrays. They're easily customizable, the package is customizable, and the current version is the result of about 3 years of iterations, going out to labs, working with labs, sort of listening to individual needs, particular needs from experienced people, inexperienced people, and we're trying to build a platform that is robust and can be used by the experts and the novice researchers out there. And obviously what's unique about this compared to anything else out there, it's a true three-dimensional array. So you can sample in X and Y and Z dimensions. The way that, well, let me go back to that thought. So I've got some samples here. Let me pass these around of the different sort of families of matrix. We do have an acute. So here's an acute matrix, and that's what's shown here on the left. And it's still a 3D matrix array. However, it's a rigid structure. So it's designed to be mounted to a manipulator and driven into the tissue and is reusable, as opposed to the chronic version that has a flexible interconnect. Who all has experience using the Utah array? Anybody? Okay, so you guys are familiar with it. And yeah, so a lot of the criticisms of that array we've taken as opportunities to improve. Like, for example, the wire bundle, they refer to it as. In our case, it's not a wire, it's a thin film, but in the Utah array, it's rigid and very rigid, and there's a lot of effort required to form it into the right shape to get it to rest exactly where you want it. And so what we've done is developed an ultra flexible interconnect that is easy to maneuver. Should also point out that we've got small animal matrix arrays, and these are the same array, just a much simpler and lower cost package, because you don't need all the titanium and protective hardware for a small animal that you do in a monkey.
How far do these are MRI compatible?
I'm sorry?
Yeah, some of them are definitely not MRI compatible.
Yeah, so I don't have an image of it, but we've got a version of the MR compatible matrix, and it's the same electrodes. The arrays are MR compatible, the cables are MR compatible. The printed circuit boards that are inside are MR compatible. What's different is the titanium versus PEEK. So it's a PEEK package.
And I just think all the arrays are available in the
Yes, exactly. Yep.
Can you explain me? So you have over there two pedestals. What's the one to the right, in the middle?
Here?
Yeah.
Good question. So this is an earlier version of the matrix, and so it had NeuroNexus connectors built into it. And then this is actually a smart matrix, but it resembles the current version of the matrix, which is a pedestal connector. So what we learned through working with various labs is the NeuroNexus connectors they're not robust enough to hold up in a monkey type environment. So they were breaking down. And so what we did is designed a
I pass it on.
So a pedestal version, which has self-aligning adapter that then has the NeuroNexus connectors on it. So therefore, if the NeuroNexus connectors fail at some point, it's an adapter. You just repair or replace the adapter.
But still, the end side of it is NeuroNexus.
They're same tech, like the BlackRock version of different adapters.
Yeah, so we have an adapter that can break it out to different types of connectors. The pedestal is a proprietary connector, as shown there. So what you need then is an adapter that is used temporarily when you're recording from the array. Actually, here Here it is here. So this is the adapter. So this is all that stays on the animal. This is a connector. There's a threaded cap that goes over the top of this to protect the circuit board. And then this adapter threads on. So we actually developed a tool that is based on a torque wrench, so that you torque it to a certain point and then it won't allow you to over tighten it. And you know that you get sufficient compression. And I'll show you that tomorrow. That's not an absolute requirement. It's just a little bit of a safety net so that you don't accidentally, by default people tighten it. It's like, well, it might not be tight enough, so tighten a little bit more. And you don't want to over tighten it. And here are photos of just that. So here's the pedestal with the protective cap that's threaded on. And then here is the adapter with 4 Omnetics connectors. So this is 128 channels coming up. So again, we've spent a lot of time going out to labs. There's about a dozen labs or so around the world, Japan, China, and at Baylor College, University of Chicago, Northwestern, NIH, that we've gone, and it's been an interesting learning process for me because everybody's got their own spin on things and what they like and don't like, and so we've tried to incorporate all of that input into the designs.
Just back to that, the picture, MRI, that label with MRI is MRI compatible.
Mm-hmm.
And it seems like you're using the same titanium screws in this case.
Well, yeah, so we provide titanium screws with the package, but as Steve can speak to, there are ceramic screws that you can use as an alternative, or peak screws, I think, even.
Ceramic screws work really work well. There's 2 different types. You have cancellous and you have machine thread.
Mm-hmm.
We like using machine thread better than cancellous. So you have Thomas recording, or you have the ones that we have. And we just find that you can get more thread into, because typically the monkey is about 3 millimeters. So you can get more thread into there. There's nice osseointegration. You can even coat it with HA, or you can even sandblast it and it'll stick better, but they work well. They're really.
And you've used them to anchor head posts, correct?
Everything.
Yeah.
Head posts,
So if they work in that,
they
the matrix would be no problem then.
You're talking about for the MR, the
Yeah.
MR stuff?
Yeah.
You have to.
So the inserter, where is that guy? Yeah, Steve was showing this. So this was another an opportunity as we were designing the matrix, was to improve the surgical implantation part of it, and to develop a way to more precisely, in a more controlled way, insert the device. And this is our inserter. It's a computer-controlled, motorized, linear actuator. I list the resolution. I think it's
0.5.
steps. Oh yeah, 0.5 microns per step. So you get ultra-fine precision. It has a speed up to 8 millimeters a second, which I'll get into a little bit more. Is on the high end. That's too fast based on the research that we did. Pass that around. And it's a vacuum tip here. So what you'll see is a plastic tip there that you hook a vacuum hose to, and that's how you attach the array to the inserters by way of vacuum.